Welcome to Breadboarding. This is video 19 in the Breadboard 8088 PC series, and it's the 7th video looking at developing the Monochrome Display Adaptor video controller. So in this video we're going to be doing just some preparations for the last push on getting the video controller fully working. We're going to be adding the CRT status register, control register, and also the Blink Clock PLD, which is necessary for doing the timing for the cursor and the character blink. So if you take a look at our block diagram that we've been using throughout this series of videos. So this is where we left the video controller in the last video, where we've wired up the character generator, shift register, and the video digital analog converter, and we tested all that and we managed to get things working with the character output in black and white. In this video, relatively simple steps in this one. So we're going to be adding a special program or logic device for producing the two clocks needed for the blinking of the cursor and the blinking of the characters, and also the CRT control and status registers, which appear in the memory map or the I/O port map on the right hand side here. So have a quick review through the PCXT schematic diagrams which have been annotated, which we covered a number of videos ago. I'm just going to pull out the key bits that we need for the blinking and the control and status ports. So this high-level diagram from the original MDA documentation, all I've done here is just expanded out the video process logic here, in that as well as the digital analog converter, we also need three program or logic devices, one for handling the blink clock, the other for handling the attribute multiplexing and some of the attribute decoding, and another one to handle all the video output logic. These first two here are by far the most complicated part of the whole design. So we'll just skip through some of the earlier sheets which are not relevant for this video. So there are a few things to note on this clocks and timing. There is a clear video signal which we can see here and which comes from over here. Now I was trying to understand what this was to do with, and this appears to be when display enable goes from high to low. So this means when there's no visible output, then this gate here produces a signal that is used to clear some of the latches and flip-flops further on down the line. Now the only issue is it was a little confusing, and in fact it turns out some of the diagrams here weren't completely accurate. So this particular chip here is in fact, when you look up on some of the other sheets, then U43 is in fact an OR gate, and this particular bit must have just been misunderstood, because I think someone transposed an S into a 5 here, and this particular symbol here is inaccurate, because if you work out the logic rules for this, this actually works out to be a NOR gate, not to be an OR gate, and that certainly caused some confusion when I was trying to work this out. And similarly, there are some mistakes up here as well, in that the overall effect of this combination of gates is a NOR, but in fact this particular gate here as part of U100 is in fact an OR gate. And again, U100 appears down the bottom here, and this is a 74LS32, which is a quad input OR gate. So again, these diagrams are pretty good, but there are the odd little mistakes which can cause a bit of confusion when you're trying to work out what's going on here. Now the other reason why I was looking at this is that when we looked at the last video, there was a little bit of half a character probably missing on the far right hand side. And the original design here did delay the horizontal sync and the vertical sync signals by one character clock cycle, and I think I might need to introduce that and see whether or not that actually makes any difference. So we'll have a look and in later videos and see if we can add that delay to horizontal sync, vertical sync, and if that makes any difference. So this is the sheet. So sheet 4 includes the CRT status port. So the status port is in fact just a buffer, in fact, and it only has two outputs. So here on the top left is the extract from the MDA documentation. Bit 0 is in fact horizontal drive, which is basically the horizontal sync signal. Bit 3 is the output black and white video. So this is actually the output going to the cathode ray tube, so whether or not there's any output bits coming out of there. According to the documentation and according to the site I'll just show you here, we've referenced this previously, the control register includes the various details and control register, and also says for the status register. And on a real IBM MDA, then bits 7 to 4 are always 1 and bits 2 to 1 are always 0. So I want to try and make this as compatible as possible with the original MDA, so I'm going to make sure that is true. Bits 1 and 2 will be set to 0 and 4 to 7 will be pulled high. So we're going to be adding this to the design. Now this is probably the most complex part of the whole thing, and we're not going to be covering every single yellow box on here. But the key thing really to look at here is at the top we have the vertical sync signal coming in. Now in our particular case this will be around 70 Hertz, because that's the refresh rate we're using for the 400 line display. And these are some dividers, and in fact what these dividers are doing are dividing the 70 Hertz down by 16 for providing the cursor blink frequency, and then a further divide by 2 to provide the character blink frequency, which is divide by 32. So in fact the characters will blink at half the rate of the cursor. Now the cathode ray tube controller chip, the 6845, does have the ability to control the cursor blink rate with settings internally, but I suspect that IBM used this external blink clock so that the cursor and the characters could be coordinated in some way. So we're going to be producing a PLD to divide down the vertical sync delay down to the cursor and the character blink frequencies. What I have also done here is annotated with the orange here. This is where the color MDA signals. If you go back to this CSIP info, then this is also the one we referenced earlier, which talked about the color MDA. So surprisingly, a few MDAs generate color as well as monochrome output, and in fact this link here no longer works, but the color functionality can be enabled in later MDAs. It identifies the chip, so U30 to U63, U63 to U64, and U64 to the 9-pin output connector. And what I have done now is I've highlighted on here, so U30, the output here of the attributes can have the foreground, background, red, green, blue and intensity. We skip to the CRT control port, and you'll see here that where those attribute signals are coming in here, then if these were wired up, so this is U63 and U64, and these were then wired up to the 9-pin connector with an appropriate monitor, then this would take the red, green, blue signals and do color. So the CRT control port is a 4-way D flip-flop. So it's not a latch or anything like that, it's just using a flip-flop, and I guess one of the reasons for this is it includes inverted output as well as the original output. So the values of the control port are over here. Now the high resolution mode always has to be set to 1, and some nasty things happened if you didn't set it to 1 with the original IBM PC. For simplifying our case, we're just going to always assume that this is a 1 and we're not going to make any use of that. Bit 1 was not officially used, but apparently this was used to control between the black and white and colour mode on some versions, so we will certainly be using this bit for switching between black and white mode and colour mode. I believe black and white mode will have this set to 1. Bit 2 is not used. Bit 3 is video enable, so when the PC resets, then this control port will in fact be reset and cleared to 0, and so until such time as video enable is set to 1, then there won't actually be any video output coming out here. And in fact this bit of logic here that takes the output for video enable and uses the reset and that output, and what this will do is it will not output any horizontal sync signals until such time as video enable has been set high the first time after a reset. So this bit of logic here appears to protect CRT monitors particular, which probably could get damaged if the wrong synchronization signals were being output. So this just means that only when the code enables video enable will the horizontal sync signal be output. Whether or not we need to bother with that in this version, with LCD monitors it doesn't really seem to be as much of a problem, but that's certainly what the original purpose of this appears to have been. And finally, the bit 5 is used to enable blinking. So if this is set to 1, then characters will blink if the attribute 7 bit is set. If enable blink is 0, then the bit 7 on the attribute will be used for the background intensity. So we're going to be adding the CRT control port and the CRT status port, And we're also going to be adding our Blink PLD, which is replacing the divider chips that was on the previous slide. So this is the shift register and the character generator EPROM. Again, there's not much here apart from this clear video was used to clear the shift register. Now at the moment, we've wired this clear signal up to reset, but we might need to look at whether we need to change this if some of the interference or video artifacts on the final version of the MDA adapter are not quite right, then that might be something we need to look at. So here's the working copy of the schematic that is almost complete now. There's probably a few minor things we might need to do to it before it'll be finalized, and then I will validate it and check that all the links and things are correct. So what we're going to be doing in this video, we need to be adding the CRT status register, which is here, the CRT control register here, and the Blink divider PLD. So I'm going to go in and have a look at each of these in a little bit more detail, and then we'll go and have a look at the board and what we need to do. So CRT status register, I've decided to use an 8-way buffer. So this is connected up to all 8 data lines. We have the input here is the horizontal sync, and in fact I've got a delayed horizontal sync is coming from all the way over here, so this is going up to the VGA connector. So you've got the horizontal sync delay, which is what that input is supposed to be. Then the other one is the video output. So this is the output from the video that's going to the to control the video multiplexer. So this just basically tells it if there's anything going on the display. And then given the other information that we saw here, then bits 1 and 2 are tied to ground. The bits 4 to 7 I've actually tied to 5 volts. So what that should mean is that this would be completely compatible with the original MDA adapter. So that's the CRT status register. So that's just a buffer that reads that information. Should just say that this is selected when the CRTS signal out of our IO port decoder. And then the other signal we got is the CRTC, so the cathode ray tube control register. And if we go down here, we can see that this is in fact a quad D flip-flop. So the 74LS175, and this is actually what the original MDA adapter used. We can see that on reset, then this clears all of these, and we can see of the outputs we've got the enable blink, we've got video enable, this is the clock input from the select, and then we've also the high res I've just tied to 5 volts always permanently. D1 is in fact connected to D2 line, and that actually provides our black and white color control. So when BW is 1, then it will be monochrome mode, black and white mode, and we're going to use this once we enable the color processing in our multiplexer here, which will determine whether or not we're using the monochrome information coming from down here or whether we use foreground background colors. Then finally we need to add our PLD for doing the blink clocks. So because the simple PLDs like the ATF16 and the ATF22 chips that I've been using, they only allow one clock signal. So the clock pin here is in fact connected to vertical sync. So that means that this vertical sync will typically be about 70 Hertz. And what we've got here is a divider, and in fact we've got Q0 to Q4 divider. So Q4 would give us a divide by 32, and the blink cursor output comes from the divide by 16, and blink character comes from divide by 32. I've also used this PLD for providing the horizontal sync input, and has the ability to configure whether or not we want to invert horizontal sync and vertical sync. So for the moment, vertical sync is just being passed straight through, it's set to 0, but the invert horizontal sync is set to 1. So this means that horizontal sync will in fact be inverted here. Now unfortunately we can't actually do any of the delays to the horizontal sync signals as part of this process, because we only have the clock of 70 Hertz, And so in fact what we'll be doing is passing this into the next PLD up here, the video out PLD, because this actually has a character clock. So we will be able to delay those signals by one or more character clock cycles if we need to. So that's what we'll be doing in the next video. So those are the three chips that we're going to be wiring in. So let's just take a quick look at the Blink PLD configuration. So this is a ATF16V8. When I've tried to program these in the past to use the flip-flops, the .D registers and things, I've had some problems, and in fact what I ended up doing is compiling this from the command line to actually find out why I was getting some of these errors and things. So if you do have problems compiling PLDs and the messages out of WinCUPL aren't normally very useful, so try using this and compile it from the command line and you might have better luck. So for this, the clock for this is going to be the vertical sync. So we've got vertical sync and horizontal sync in. We have 2 pins to invert vertical sync and invert horizontal sync, and then we've got the vertical sync out, horizontal sync out, which will be inverted if one of these pins is high, and then we've got a counter here that goes from Q0 to Q4, so that's divide by 32, and we're using that for the blink cursor and the blink character. So we've got the pin definitions here. Then the horizontal sync out, this is a formula that will just invert the value of horizontal sync based on the invert horizontal sync, and the same for vertical sync. And then down here we've got our flip-flop, D-type flip-flops with the conditions on it, which basically gives us a counter. So these are pretty standard conditions that you would include to make a counter or a divider. So this is going to be dividing by 16 for Q3 and 32 for Q4. So I won't show programming this. I've shown lots of programming PLDs, so I'll just program that and then we'll fit it to the circuit. So here are chips we need to add. So this is the buffer, and that's going to be going between these two chips here. So hopefully we've left enough space in the last video to add that in. It will need to also be wired into the data bus here. So we might need to find some spare data bus lines that we can wire that into it there. And there's only there's only 2 signals that are coming from there, one to horizontal sync and the other to the video output, which will wire up to probably the output of the shift register for the moment. Then we've got to put the quad flip-flop, and that's just this is going to be the control port. So that's going to go below the attribute latch. So the attribute latch is going to go here, and we're going to put that down there. Then finally the blink clock is going to go down the bottom here. So just going to wire those up. I'm just going to put in the buffer for the CRT status. Put in the power lines. Then we need to put the data feed from down the bottom of the board there. Now we're putting in the link for the port select. That needs to be tied to ground for the other chip enable. Now we're just putting in the output for the video for one of the inputs there. We'll leave the wire there for hooking up to horizontal sync at some later point. Just putting the pull-up resistors in there. So now we're putting in the CRT control port. So there's various data lines, the reset and the chip enable. So these are the D2, D3 and D5 coming in from there. We're just putting in the chip select there. Need to put in the reset. Now we're putting in the Blink PLD, so just wire up the power lines there. Now we need to wire in the pull-up for the invert or not. So vertical sync is normal and horizontal sync is inverted. Now we need to wire in the horizontal sync and vertical sync. That's the vertical sync, including going to the clock. Then wire in the horizontal sync, vertical sync there. All done. So fitted the CRT status register, control register and the blink clock. I'm not going to do any testing of these at the moment. We'll do that as part of the next video where we're going to be adding the attribute latch, attribute multiplexer and the video output PLD, and that should allow us to get a fully working monochrome display adapter, and depending on how much time we have we'll do the black and white testing, and I suspect we'll need an additional video to do the colour testing. So if you don't want to miss out on future videos, please hit subscribe, and if you've found the content interesting or useful, please hit like. It just helps to make the videos available to a wide number of people. Thanks for watching.